So on this first problem, on part A, we're just asked to draw the electric field, the magnitude of the electric field due to this, it's like you call it a quadrupole, I guess it's two dipoles on the same axis. So everything is on, looks like the x-axis, I guess. And the relative magnitudes of the arrows should be correct. So longer arrow means larger magnitude. So the magnitude, first I'll explain the magnitude. Magnitude of the point A is going to be larger, the arrow is going to be longer because it's closer to this positive charge here. And then the one at B is going to be a little bit shorter, uh, smaller magnitude. So, and then the direction, I know that the electric field is going to go point away from a positive charge, and since the positive is closer to it, um, then we're going to be pointing away from that positive charge. So another way to look at it is you can kind of do the electric field to each individual charge, and if you add them together with the correct magnitudes, you're going to get a positive because this positive charge is closest. So then for part B, what is VB minus VA? So pretty much I just explained this, that as if you subtract these two from each other, you're going to get a negative because the smaller positive value minus the larger positive value is going to be a negative. Uh, and then the one that I got wrong here, pretty much what I did on the test was just put uh, the formula for the potential in here along with the E that you gave us at the top. Um, I think that what I did wrong was not integrating it out, I guess. So let's see, I gave it a try here. I kind of need to look at it. So I ended up with h over 4 pi e naught times 1 over 3b cubed minus 1 over 3a cubed. And the negative sign went away because I had a negative in the denominator here. Uh, that's pretty much it. The only thing worth explaining, I guess. Honestly, I'm still a little bit confused on that, but I'm just trying to take this one step at a time here and figure everything out. So then on the next problem, we have let's see, the dipole placed a certain distance away from a insulator, so a sphere, a neutral insulator. And we were asked to draw the charges. I think the first time I drew it, I just drew positive, negative going across the top, and then positive, negative going across the bottom, just trying to even it out because I know that in the insulators, your electrons aren't as free to move as they are. Your charges, your electrons aren't as free to move as they are in a conductor. So here I just put the charges on the inside of the ball uh, and opposite to this dipole here. So since the dipole has um, negative on the right, I got the negative on the left, and positive on the left, I got the positive on the right. Approximate charge distribution, yeah. And then we're swapping it out with a conductor here, a metal sphere, and we're asked to draw the electric field due to the dipole and the electric field due to just the charges um, on and inside the sphere here. So the first one, to me, I completely understand why we have, so ED, electric field dipole, is pointing to the right here, because if you take the positive charge, the positive is going to be pushing it kind of down and to the right, and then the negative is going to be pulling it up and to the right. And if you take the kind of add them together, you're just pointing to the right. And then the uh, electric field due to the charges in and around, and in and around the ball is going to be going to the left because the negatives pull the charge towards it, and we have more negatives on the left, and then the positives push it away, and we have more positives on the right. So it's just going to the left. And then if you cancel those two, I mean, like if you were to add those together, which would be your E net, you would get 0 because you have pretty much like, I guess you can look at this as -1 on the x-axis, and you can look at this as 1, and if you add those together, it's just 0.